In this pre-calculus algebra topic, we'll look at transformations of functions. When you know the basic form of some basic functions, then you can look at the equation of that function and determine some really important information about the graph. For example, you can tell whether the graph moves up or down from the basic function, left or right. Sometimes it's shrunk or stretched. But you could see this topic, transformations of functions. Are you ready for this? As a shortcut. Rather than plotting points to graph every function, you could use this shortcut instead. I think that many of you who are watching this video will find this to be very helpful. Have you ever seen special effects in a movie where a person or object is continuously transformed into something different? In a movie, this is called morphing. In math, we can use transformations of a known graph to graph a function with a similar equation. This is achieved through horizontal shifts, vertical shifts, reflections across the origin, or I guess I should say reflections about the origin, reflections across the x-axis, reflections across the y-axis, and from stretching or shrinking. Those are the different transformations we'll look at to some functions when we look at the equation. In Unit 2, you'll see, here we are with number 5, that this learning objective, describe how the graph of a function can be the result of vertical and horizontal shifts, stretches, compressions, and reflections of the graph of a basic function. So this is on our set of learning objectives, which keys me into this important point if you're concerned about passing a final exam. This topic is certainly going to show up on a final exam. Let's start out with a true-false question. True or false? The graph of the identity function, f of x equals x, and the standard cubic function, g of x equals x cubed, have the same type of symmetry. The answer to that question is true. They're both symmetric about the origin. Let me show you that. So if I look at f of x is x, and then I look at f of the opposite of x, that would be, so one way to look at this is I go to the x, right? And in place of x, I'm going to put the opposite of x. And the opposite of x is the opposite of f of x. I know the first time you do this, this might feel a little confusing. But if I looked at f of x and said, what's the opposite of that? The opposite of f of x would be the opposite of x, right? So that's the opposite of f of x. But in this case, f of the opposite of x also came out to this opposite of x. So we can see that f of the opposite of x was the same as the opposite of f of x. So what we say about this function is that it's odd. When the function is odd, it's symmetric about the origin. What that means is this: if I have a graph, let me take the graph of let me take just this part of the cubic function. Now, if I reflect that across the y-axis, I get this line, right? So if I fold on the y-axis, and now I'm going to take that and fold it again. I'm going to fold it on the x-axis, and the reflection would be here. So what I'd say about this function, by this function I mean this whole function, what we say about that is it's symmetric about the origin. We could see that the same thing happens for the line f of x equals x, and that's the one we proved first. Let's look at the algebra now behind g of x. If g of x is x cubed, then I could say that the opposite of g of x, the opposite of that function, would be the opposite of x cubed. Remember, this opposite, this green negative out in front, isn't being cubed. The negative is not attached to that 3, so this is the opposite of x cubed. If we expanded it, it would be this. There's only one negative there, right? So that's our opposite of g of x. If this function is odd, and therefore has symmetry about the origin, then g of the opposite of x is also going to be the opposite of x cubed. So let's see what happens if I replace the x with the opposite of x. I'd have the opposite of x cubed. Well, that's a little bit different when I expand it, but let's see how it simplifies. We have 3 negatives being multiplied. So when we have 3 negatives, couldn't we say that that's the opposite of x times x times x, which is the opposite of x cubed? And so this is, in fact, odd. Whenever the opposite of f of x is equivalent to f of the opposite of x, we call that function odd. Now let me tell you, this is one that you just have to know. You do have to know that that's, by definition, that's what odd means. And if I'm your teacher and I'm giving a quiz, let me tell you that that would certainly be on a quiz. This is what we would call, and some people would call this a library of functions. Some books I've seen call this a library of functions. And in our textbook, it's just saying common graphs. Let's look at each of these. We've got f of x equals a constant, like f of x equals 1.5. We get a horizontal line. F of x equals x, we get that line that cuts through quadrant 1 and 3 at a 90-degree angle. F of x equals the absolute value of x, gives us a v, where the vertex is here at the origin. F of x equals x squared gives us a parabola, where the origin is the vertex again, just like it was for the absolute value. See how similar the absolute value and the x squared are? F of x equals the square root of x. Looks like this. You could do this by plotting points. The square root of 0. Let me show you that in case you're looking at these. How did they get these graphs? F of 0, when x is 0, square root of 0 is 0. When x is 1, the square root of 1 is 1. And then I could do 4. The square root of 4 would be 2. With those 3 points, I've got a good handle on that graph. And then f of x equals x cubed. You could do point plotting again. When you cube 0, you get 0. Cube 1, you get 1. Cube negative 1, you get negative 1, and so on. And then we could do the same for the cube root. It is important that you could graph each of these 7 functions and be able to specifically plot at least 3 points on all of them. So for an absolute value or a parabola, I'd use the points 0, 0, 1, 1, negative 1, 1. But notice the difference. For the absolute value, we get a v. For the parabola, the x squared, we get a rounded letter, more like a u than a v, but it's not a u. And if you had a blank piece of paper and you were asked to graph these 7 functions where you were just given the function, so here's f of x equals x, f of x equals c, f of x equals the absolute value of x, and so on, for all 7 of these functions, you should, from a blank paper, be able to graph all 7, I'm going to say in 3 minutes or less, in 3 specific points that you should be able to put on the graph. To do that, you simply need to practice this. You need to know a couple of the points. You can always do point plotting, but in addition to point plotting, you have to know the general shape of the graph. So that's the first step, to be able to graph those common functions. Next, we're going to look at some different transformations. This chart comes right out of your book, and I'd recommend that you become familiar with this chart. We're going to start with vertical and horizontal shifts. Use a graph of f of x equals x squared to obtain the graph of g of x equals x squared minus 1. So here's what I want you to notice about this g of x. Do you see that this g of x is our f of x function, our x squared minus 2? It's our g of x is f of x, which was x squared, minus 2. So we start with our f of x. So going back to the previous screen, if you know the basic function, I'm going to start at the origin 0, 0. 1 squared is 1, 2 squared is 4, negative 1 squared is 1, negative 2 squared is 4, and although you could say it looks like v, it's not. It's a parabola. It's an x squared. So I need to know that it looks more like this. I'm going to do that up through the part of the graph that we're given. So when you're given the grid, you want to finish all the way to the ends there, and I know it's going to keep going there. Now, if I'm going to take this minus 2, what that's saying is that we're going to move vertically down 2 units. So each of these points goes down 2. So this point 1, 2. This point 1, 2. The vertex 1, 2. 1, 1 becomes 1, negative 1, because we go down 2. 2, 4 goes down 2, so we're at 2, 2. And now connect those dots, and we'd get this function. A little bit off on the end point here, because it would have actually reached this point specifically. But we get this parabola that looks just like our blue parabola, but it's moved down 2 units. That's a vertical shift down. Before I turn the page, if we look back here, do you see this g of x equals the absolute value of x plus 3? Our general function, our common function, was this absolute value of x. And then this plus 3 meant, you guessed it, we're going to move up 3 units. So we take the 0, 0 and go up to x equals 0, y equals 3. Let's look at horizontal shifts. When we put the shift, the change, inside the function, so if you looked at this in function notation, f of x is being defined as x. What we're doing here is f of x plus 4. It's not that we've got our function f of x and we're adding or subtracting something to it. It's what's on the very inside of the function that's being altered. So we have the absolute value of x plus 4. So in other words, that shift is happening inside the function. When we see this, it's going to be a shift left and right. This could be a little confusing if you just go by memorizing, but if you were to plot a couple points, what you would see is that if our general function is the absolute value, so let me graph that, the absolute value goes through all these points. I didn't do the right side very well. It hits through here like a 45-degree angle, or at a 45-degree angle. So there's our f of x equals the absolute value of x. If I do this transformation plus 4 inside, you might think, oh, positive 4, it's going to go right 4. No, you've got to go in reverse. We're actually going to move left 4. And once I have that vertex, I can just start going up from there. So it would look like this. Notice that this goes left 4, even though it's a plus 4, a positive 4. When we have the change inside the function, it goes the opposite direction. If we look to the right, to this problem that was already done, here's our f of x equals the square root of x. In this shift, minus 4 is going to move the graph right 4. So we go from 0, 0 and go right to 4, 0. So that's a vertical and horizontal shift. I hope that this video on vertical and horizontal shifts has been helpful to you. If you want to see more shifts, such as reflections and shrinks and condensing and stretching. So shrinking and stretching, there will be a second video, but I'd encourage you to stop the video now and practice some of the examples from your homework that use vertical and horizontal shifts.